Okay, good afternoon, everyone, and thanks for joining us this Thursday afternoon before what I'm sure for a lot of you will be a long, nice weekend. So thank you for being here for today's webinar, organized by BBI International and Ethanol Producer Magazine. From our studios here in Grand Forks, North Dakota, still covered in snow. We wish it weren't. Thanks again for taking time out of your day here to pick up this webinar series with ICM Inc. This is the fourth part in this webinar series, and I think you'll enjoy it. My name is Tom Bryan. I'm president and editor-in-chief of Ethanol Producer Magazine, and I am your host this afternoon and happy to get things rolling. I'm joined today by Chuck Gallop, Director of Innovation at ICM Inc., who will be giving a presentation titled Lowering Your Carbon Score While Diversifying Revenue. Chuck's presentation is, again, the fourth in this series from ICM on its Advanced Processing Package that's now been adopted and being installed in multiple U.S. ethanol plants. As many of you know, this APP platform is essentially a suite of integrated specialty equipment, a sort of bundle of customized and proven technologies that together, when combined, enable ethanol plants to achieve a number of positive outcomes that all sort of orbit around this exciting opportunity of high protein feed. In previous webinars, ICM has explained with precision how the equipment in the package works, and more specifically, how it can work with your current plant setups. I want to mention that we've also published an article on the APP system in our May edition of Ethanol Producer Magazine. That article hasn't come out in print yet, but it is posted online. It's titled Equipping for High Protein, so you can find that on our website, ethanolproducer.com. So again, we will get started with this popular series here. Today, I believe Chuck will be talking about the technology and installation of APP in the context of not just what the technology yields in the way of products and product diversification, but how it can boost efficiency, lower energy consumption, and ultimately reduce the CI scores of the ethanol that you produce, which is, of course, what everyone's talking about right now. Efficiency, displacing fossil energy use, and in some cases, straight up carbon sequestration. Before we get started today, I want to be sure to mention that this webinar is being recorded. It'll be available online, like all of our webinars. I think we'll get this one posted probably early next week on ethanolproducer.com, and ICM will also have it available along with the other three webinars on its YouTube channel that is listed on our screen. When the webinar is posted, you'll be able to review it. You can watch it again, share it, and of course, reach out to Chuck if you have any questions later on. But there is actually no reason to wait too long to ask questions. You can do that right now today. So if you have a question while Chuck is presenting, please type that into the webinar platform. We'll see your question. We'll be able to address that just as soon as the presentation is over. So we'll hold all those questions until the end and then address them. For those of you that might have questions that are, private or better suited to be asked offline, we're happy to help you get in touch with folks at ICM to make that possible. We can do that. And with that, we will now hear a message from ICM before Chuck gets started.
ICM is proud to sponsor Looking to the Future Today, ICM's approach to efficient product diversification, a webinar series hosted by BBI International. Since 1995, ICM is focused on innovating and developing new technologies to support the production of renewable fuels and animal feed. More than 100 biorefineries worldwide have adopted its proprietary systems, designed to help plants realize higher profits and better operational efficiencies at every step of the process. A global leader in the biofuels industry, ICM offers design, engineering, manufacturing, implementation, and plant support. To date, ICM has completed more than 5,500 projects across more than 300 locations, including over 30 plant retrofits. Want to know more? Visit icminc.com or any of these social media platforms.
Good afternoon, Chuck Gallop here. I'm the Director of Innovation at ICM, and I want to first take a minute and say thank you very much for taking some time out of your day to join us on this webinar. And as Tom said, we'll be taking questions at the end of the presentation, so if you have any questions, please don't hesitate to submit those. Otherwise, you can visit us at booth 821 at the FEW coming up here in June. Also, this four-part series is on ICM's YouTube channel. It's all lowercase, ICM Global. So you'll be able to go out there and listen to the first three or re-listen to this one as well. Otherwise, you can visit Ethanol Producer Magazine's YouTube channel at Ethanol Producer Magazine, and this webinar series will be there as well. So again, thank you very much for joining us today. So what we'll be talking about today is how you can lower your carbon intensity score while diversifying revenue. More specifically, how can you increase the revenue of the plant while increasing efficiency? So what we'll talk about is ICM's vision for biorefinery, how we approach diversifying revenue, and increasing efficiency throughout the plant. So we'll also talk about the different value-added products within this presentation. And at the end of this, we'll wrap everything up into what that means for your plant. Specifically, what happens to the bottom line of your CI score and potential revenue generation by employing ICM's APP process. So there are quite a number of ethanol plants out there right now that produce dried distillers grains from the whole kernel corn. And what we want to do is take a look at how we can break that pile of distillers grains into multiple piles of higher valued co-products and increase the efficiency of your entire ethanol plant as you do this. That way you can maximize profits. So when we take a look at that corn, we're going to convert that starch into corn to ethanol. And then you have a distiller's grain pile, which is roughly 30% of that corn that you purchase. But how can we break that VDG pile into high protein feeds and high fiber, high energy feeds and improve the efficiency of the plant and reduce your carbon score? So we do that by packaging up 4 independent technologies. And we'll go through these one at a time and explain what each one of these technologies do, but how each one of these technologies contribute to the energy efficiency gains and the lower CI score. So we'll talk about selective milling technology, or SMT, fiber separation technology, FST, feed optimization technology, or FOT, and then TS4, which is thin stillage solid separation system. Together, these 4 combined make up the Advanced Processing Package, or APP. So we'll start off by taking a look at a baseline ethanol process. Here's a very basic block flow diagram that most of us are familiar with. And it starts off with milling of the cereal grain or the corn through slurry, liquefaction where the starches broke down to sugar, and then fermentation, distillation, and dehydration. And then solid liquid separation, which is the decanters, evaporation, and then ultimately the dryers. So, and we'll go into this in a lot more detail of why we're doing what we do, how we augment the process to generate differentiated co-products of higher value, but where the energy efficiencies come from each step of the way. So we're going to start off by looking at the 4 processes, the 4 technologies that make up APP, or the Advanced Processing Package. as they're integrated into that baseline ethanol plant that we just looked at. So we still have corn, we still have milling, we still have slurry, but off of liquefaction, we have SMT and FST, or selective milling technology and fiber separation technology. So this process, you can integrate these two technologies individually or combined together, which removes the fiber pre-fermentation, bypassing the rest of the process. Now, after fermentation and dehydration, the next technology is feed optimization technology, or FOT. This is a unique process that enhances oil recovery and continues to intensify the protein concentration, allowing greater than 50% crude protein, and TS4, or thin spillage solid separation system, then removes any remaining yeast and fiber and protein and adds that back to the 50% crude protein to make a yeast-enriched PROTOMAX, and that's depicted here on the screen. So this is a really high-valued product here. The end result is distiller solubles of higher concentration, higher distillers corn oil yields, and increased plant efficiency. So how do we do that? Well, first we start with the milling step. The milling step is by far the most important step of the entire process. And your first step when we address this cannot be the limiting step or the limiting process for the technology. Henry Ford had said years ago that you can have any color car you want as long as it's black. And so when he made that decision to make every car black, he made decisions for his assembly line. First, black is not the first choice of color for every consumer. Two, black is the hardest color to paint. And three, black is the hardest color paint to hide any bodywork imperfections. So by him selecting the color black for every car, that means his painters had to be superior than anyone else, and his bodymen making the cars had to make sure there's no imperfections, otherwise they'd show. So making that selection for a black car set the standard for everything else downstream. The way we grind this corn also dictates how everything else in the process will interact, and it will also impact the outcome. So ICM takes a unique approach to the milling technology, and we are looking for, in this process, consistent milling or consistent particle size granulation. Not uniform granulation, but consistent. If it's consistent, then we can optimize every downstream process from there. Okay? Here's an example of what we're talking about. On the right-hand side, you'll see a fine grind where that corn has just been pulverized to a fine grit-like consistency. On the left-hand side, which is labeled right-size grind, is something more like what we're looking for. And so we'll get into and explain why we're starting off with right sizing of the feedstock through the process. Okay. So after we grind the corn and we slurry it and it's liquefied through traditional means, then from there we go into selective milling technology. From here, you're wet milling this corn to expose more of the starch away from the fiber and the proteinaceous material, and then we're also expressing the fat out of the corn germ as well. So this is a way to reduce the amount of residual starch and fat that ends up on the protein post-fermentation and distillation. After selective milling technology, then we go to FST, or fiber separation technology. Now we'll get into this in quite a bit of detail as we go through the presentation. But when we're looking at this, we have the selective milling technology, which includes a multi-zone screening apparatus and a milling technology within that process. A secondary milling step will expose that starch and express the fat from the germ. And then the final step of FST is a proprietary rotary press that ICM has teamed up with Fournier Industries to produce, and that apparatus is phenomenal. So I want to draw your attention to that rotary press and help explain why this is a unique apparatus or device that we use within the fiber separation technology package. And this might help explain how we're able to improve our energy efficiency as we remove fiber from the process stream before fermentation. Now, I've given presentations a bunch of times around fiber separation technology, and I tend to use the phrase that helps explain why we separate that fiber. And this phrase is that nobody eats the box that the pizza comes in. Although you buy the box with the pizza, nobody eats the box. And that's what fiber separation technology does, is it removes the fibrous material or the unfermentable material from the rest of the corn, and that fiber bypasses the entire process. Such as when you buy that pizza, you take the pizza out of the box, you throw the box away. In this case, we just move it on past the process. And one of the apparatuses used is the rotary press. Now, we're looking at 3 pictures of the rotary press here on the left-hand side. You'll see that there's multi-channels on a single shaft, and the middle picture and the right-hand picture will show what that looks like from the front. Each one of these channels will receive a fiber slurry and dewater that fiber slurry. Now, we'll talk a little bit in the coming slides how dry we can get this fiber and why it matters. But essentially, fiber separation technology is removing the fibrous material from the fermentation stream, freeing up more fermentation capacity, more heat exchange capacity, alleviating electrical load on pumps and heat exchangers and centrifuges. So we'll get into that in a upcoming slide here. Here's what that rotary press looks like. It's a depiction showing that the rotary press is built in segments with 2 channels equaling a cassette. Now, what's really cool about this rotary press is that it washes and dewaters the fiber that used to go to the fermenter and to the beer well in the beer column. Now, this fiber is now cleaned and washed and dried. In this case, we're able to achieve upwards of 45 or 46% solids on that fiber. If we didn't remove this fiber using the rotary press, and that fiber had went through the rest of the process and to the centrifuges, that fiber would then come out of the decanters, the whole stillage decanters, at roughly 37 to 38% solid. But because of the rotary press's unique ability to dewater this fiber, we're able to achieve the 45 to 46% solid. Now, the other interesting thing about this rotary press is it uses very little connected horsepower. To process all of the fiber stream and water, we're using between 40 and 80 horsepower, depending on how many motors and gearboxes there are. If you have 8 channels in a row, we would use 1 gearbox and motor. If there's more than 8, then we would have another gearbox and motor on the other side driving the channels from both sides. So you'd see between 40 and 80 horsepower. And the max speed of this press is between 4.5 and 5.5 RPM. Whereas in a centrifugation process, for the same flow rates, we would see somewhere between that 400 and 600 connected horsepower, and each one of those decanters will run between 2,800 and 3,200 RPM. So it's a substantial difference in how fast these machines run and the amount of connected horsepower. But more so than that, we're decreasing the capital cost and the operational cost for the rotary press over decanters, but we're able to dry this to a much drier product. That will alleviate hydraulic load on the dryers later on. So here is a video, and it might be difficult to see, but you have rotating plates inside the rotary press that dewaters the fiber, and you'll see the water pass through that screen in that sight glass there. And you can see how slow this rotary press really turns it. In this case, it's probably running in that 2.5 to 3 RPM range and achieving mid-40s% solids consistently. So this is a patented process, and we're pretty excited for this technology and the partnership with Fournier. On the left-hand side, here's a video of what that fiber looks like as it comes off the rotary press. In this particular case, that fiber is in that 4% residual starch range, somewhere around 18 to 20% protein and low fat. And this fiber will bypass the fermenters. Now, when that fiber bypasses the fermenters and goes right to the dryers or to the wet pad, it will free up roughly 10% of your fermentation capacity. So now you have more tank capacity and a drier fiber and a cleaner fiber and more centrifuge capacity. This fiber didn't pass through the centrifuges off of the whole stillage, so now you have more centrifuge capacity as well. But what does all of this mean? Well, it means that by not eating that pizza box, it frees up capacity through the rest of the process, that you get to purify the protein and have a higher oil recovery yield potential because the fiber wasn't carrying protein or oil out with it. So the rotary press, again, only uses between 40 and 80 horsepower, depending on if it's 1 or 2 gearboxes and motors versus 400 to 600 in this particular application. We also save energy by not having to pump that fiber, by not having to heat that fiber up or cool that fiber down or agitate that fiber. We also free up capacity in the beer column or the beer stripper because that volume in that fiber has bypassed the beer column. Now, when we look at what all of this means and we apply some math here, we're looking at roughly an 800 BTU natural gas savings per gallon of ethanol because we remove that fiber. Now, there's a very conservative number here because what it's based off of is raising the solids of that fiber from 37 solids from the decanter to 40% solids, and 40% solids from the syrup. But when we go higher than that 40% solids on the syrup, or we go higher than the 40% solids on the fiber, then this number grows substantially. So right now we're looking at 800 BTUs per gallon based on these very conservative numbers. So that's SMT and FST utilizing the proprietary rotary press. The result by pulling that fiber out is now you have a defibered liquefaction that goes through fermentation and distillation, which means that that fiber doesn't go through the beer column, which means now that the whole stillage has been defibered and your whole stillage decanters no longer have to be adjusted for that fiber volume. That fiber has a huge impact on how the decanters perform. So the next step of the process is to optimize the decanters. And we do that by teaming up with Fournier, or Flotwig, and optimizing the internal components of that decanter to be more efficient so that we can separate the suspended solids from the whole stillage. Now, those suspended solids are high protein, upwards around 50% crude protein or higher. The changes that were done to those decanters You see in a stepwise progression here in these pictures, we start off with the original scroll, and this is what most of the decanters out there have, no matter who the manufacturer is. This is what those scrolls look like. But a few years back, Flottweg had improved the scrolls by going to a slotted scroll, and this was to improve the throughput and the operational consistency, allowing a drier cake and a cleaner centrate. But fast forward a couple of years, and Flottweg had produced this exclusive FOT scroll that we use in the APP process that could also be used for our FOT oil recovery process as well. But this exclusive FOT scroll allows us to increase the throughput and increase separation efficiency. So we see a reduction in electrical use and a much drier cake coming out of those decanters. This video is depicting how dry that cake is and how flowable that cake is coming out of those decanters. This is what the PROTOMAX looks like coming out of those decanters before the Sedicanter cake is added to it and it's dried. So you can see this material is really dry and flowable. FOT will produce a washed protein where the oil, the dissolved solids such as carbohydrates, the salts, glycerol, and organic acids are washed away from the proteinaceous material, and those organics are washed back into the process, resulting in a clean, high quality, high protein feed product. Because of the exclusive scroll, we're able to achieve as much as 45% solids coming out of the decanters of the FOT process versus a traditional 37% solids. And by removing that water from those solids will result in a much lower energy usage at the dryers. How much? Well, when we look at a traditional decanter, that decanter will produce somewhere in that 37 to 38% solids cake. In this particular case, with FOT, we're able to remove more than 40% solids. We can go up to about 45% solids. But if we use a 40% solids number, we go from 37 to 40%. We're looking at a 547 BTU, or roughly 550 BTU savings of natural gas per gallon of ethanol. That's substantial. So what's next? When we look at what we've done so far, we've right-size milled the corn, we've wet milled the corn, we've separated the fiber away from the protein and carbohydrates and oil. The protein, carbohydrates, and oil have went through fermentation. FOT has separated the proteinaceous material from the water and oil and any fine suspended solids. Next, we need to remove the rest of the fine suspended solids from the centrate by use of TS4, or the thin stillage solid separation system. So what this does is we will take the centrate off of pass 1 of FOT. There'll be a preparation to that feed stream, and then it'll go into a Sedicanter. So these Sedicanters are a horizontal decanter like centrifuge that operate at high G-force and are capable of removing fine suspended solids just like a stacked disc centrifuge. Only these machines are capable of producing dry cake rather than a flowable slurry out of the decanter. What this does is it removes the fine suspended solids, and then that centrate off of the Sedicanters then go to the evaporators. The Sedicanter cake which is really high in yeast and yeast bodies, will then meet up with the cake from the second pass FOT to make an enhanced yeast with cake, or enhanced protein with yeast cake. Okay, and we call that PROTOMAX. Here's an installation of Sedicanters. This installation is running roughly 700 gallons a minute of flow and is able to recover a substantial amount of the yeast and protein and fine fiber from that centrate. So this is the third step in our continuous dewatering process throughout APP. And these Sedicanters are a Flotwig produced centrifuge. They're amazing. They're continuous flow. And the cake that we recover off of these Sedicanters is upwards of 30 to 32% solids. So when we remove this cake, and here's a somewhat of a hypnotic video as you watch this, this is the cake that comes off of the Sedicanters that is comprised of yeast bodies. It has fine fiber in it, and it has fine protein in it from the corn. This cake is about 30% solids, and it's removed from the centrate and goes directly to the dryer with the decanter cake off of FOT. When we remove these fine suspended solids from the centrate, it allows the centrate to go to the evaporators and be concentrated to higher concentrations. Instead of 35% solids or 40% solids, we can see higher syrup concentrations, upwards of 50 and 55% solids, and even higher than that. So it's this material that's being removed from that centrate that allows the centrate to be concentrated to higher solids, and at the same time it reduces the viscosity of that syrup. When we reduce the viscosity of that syrup, what we'll see is that the syrup flows more freely through the recirculation pumps and the falling film evaporators. We'll see as much as a 10x reduction in syrup viscosity. So what that means is that your evaporators become more efficient. When we've increased the efficiency of the whole stillage decanters through the employment of the rotary press, and we've increased the efficiency of the decanters through the employment of the improved scroll, and we've removed the suspended solids from the centrate, improving the efficiency of the evaporators, the end result is an overall reduction of hydraulic load to the dryers. So what we're showing here is that when we remove those suspended solids and that centrate spends a little more time in the evaporator, you see more color bodies here, but the syrup is thinner. It has less viscosity. Okay. So the water concentration in that syrup will go down, or the solids will go up. In this particular case, we go from roughly 35% solids, and we can be as high as, in this case, we're showing 70% solids, and we've seen concentrations higher than 70% solids. On the surface, that doesn't sound very impressive. But when you add this syrup to the fiber, or through a traditional distiller's grains process, you add a 70% syrup solids to that. That means in the dryer, you only need to go from 70% solids up to 88% solids, or 12% water. It's very little water that the dryer needs to remove to achieve 12% moisture or 88% solids, versus a traditional syrup, which is 35% solids or 65% water. So essentially, we're taking advantage of the energy efficiency of a multi-effect evaporative system that almost all of these ethanol plants have to reduce the hydraulic load to the dryers. How much? When we look at removing those suspended solids from the centrate, through the Sedicanters or TS4, and we improve the energy efficiency through the evaporators because we've reduced viscosity. We see a net reduction of water to the dryer, resulting in about 850 BTUs saved at the dryer. So again, that's going from 37 solids to 40% solids at the syrup as well. When we put all these technologies together, we have ultimate control and flexibility of our end products. This is where diversifying that revenue comes in. Fractionating that distiller's grain pile at the bottom of the screen into higher valued products such as Sol brand, which is the fiber, and the Sol Max, and the PROTOMAX, which is your 50% yeast enriched protein. Okay, so we are now making multiple products worth more to the bottom line than a singular product that has feeding limitations. So what does this do? Well, it maximizes your market potential. And so when you employ APP, you have flexibility of how much PROTOMAX you produce. If you want to continue to make a traditional distiller's grains at 11 pounds of distiller's grains per bushel of ground corn, there's enough protein in there to make 3 1/4 pounds of 50% protein. Okay? So essentially, we're taking 14 1/4 pounds of distiller's grains and then making 3 1/4 pounds of PROTOMAX at 50% protein and 11 pounds of traditional distiller's grains. But you have the flexibility if you want. You can choose not to make any distiller's grains and make 9 1/4 pounds of Sol brand, which is a energy dense fiber, and 5 pounds per bushel of 50% protein called PROTOMAX. Now, here we've outlined that you make 3 1/4 pounds in traditional distiller's grains, 5 pounds of PROTOMAX and no distiller's grains, or anything in between. So if you wanted to make 4 pounds of PROTOMAX and something that has higher protein than Sol brand but less protein than traditional distiller's grains, that's at the plant's discretion. It's what the market will support. So we give you the flexibility to produce whatever protein products you want to, or protein deficient products that you want to. You have that flexibility. So how does it stack up? So when we take a look at other high corn-based proteins that are available in a commercial market right now, our PROTOMAX stacks up very nicely. So we're looking at protein content. Fat content is just a little bit higher, but that's amazing energy. As far as amino acid profile, we look spot on compared to other commercially available products. Amino acid digestibility for poultry is spot on. Protein for dairy is, you couldn't get much more aligned than that. NDF, or non-digestible fiber, is spot on. And then the digestibility of that is also spot on. So what we're showing here is that we have taken a unique approach and employed 4 different technologies that have been combined together in a suite to produce PROTOMAX, which stacks up almost identical to what other products you can buy on the market. Okay. When we take a more myopic look at what this amino acid profile looks like compared to corn versus distiller's grains, and again, soybean meal. Okay, so when we look at feeding corn, the lysine is unbelievably low, the methionine and threonine are low, so you have to consume a lot of corn to get there, but you have too much carbohydrates, too much fat. In distiller's grains, you have very little carbohydrates, but we still don't really have enough of the other amino acids, the essential amino acids. When we look at soybean meal, this is really the benchmark that we compare against. And PROTOMAX, as compared against soybean meal, stacks up very nicely. So we're able to produce all of this through traditional gas-fired rotary dryers. ICM is designed and built over 400 of these dryers, and most of the ethanol industry has these gas-fired dryers employed right now. Our technology enables the dryers, the gas-fired dryers currently used to produce distillers grains, to be repurposed to produce PROTOMAX and Sol brand. Our approach to this is unique in the fact that we don't want any stranded assets and don't want you to have to buy additional dryer technology. So we have been producing PROTOMAX for a couple of years now through the traditional gas-fired ICM rotary dryers. These dryers work wonderfully for PROTOMAX and Sol brand. So when we add all of the energy savings up, when we start looking at the dryer fiber coming out of the rotary press and how much water was removed from that fiber, when we look at how dry that PROTOMAX was coming out of the Flotwig decanters, and we look at the amount of water that's reduced through a more efficient evaporative system, we see a 2,100 to 2,200 BTU savings per gallon of ethanol. Now, these are very conservative numbers, okay? And we want to show conservative numbers because not every plant runs the same, but these are real numbers. So when we look at 2,100 to 2,200 BTUs per gallon of ethanol, that's substantial. And although we've added additional equipment, additional connected horsepower, then the net result is reduced electrical demand, meaning that because we've pulled the fiber out of the process, everything downstream from FST and the rotary press is more efficient and uses less horsepower. When we improve the centrifugation, everything downstream of there requires less horsepower. The net result is a 5% reduction of electricity per gallon of ethanol produced. That too is substantial. So what this shows is that when you employ our multifaceted, unique approach to producing diversified products, we can not only produce amazing diversified products such as a PROTOMAX, but we can do it while reducing energy demand through your plant. We can do it by and at the same time reduce natural gas demand at the dryers, which increases your overall plant efficiency. This will reduce your CI score. It shows between a 2 and 4 point CI reduction. And when you take that to real dollars and cents, we show that you're between 3.2 and 6.4 cents per gallon in carbon credits. Now, there's a little caveat to that. Here we're valuing the 6.4 at $200 per ton, but current market shows it at really $130 or so per ton. So you're in between that 3.2 and 6.4 cents per gallon. And you've produced a diversified product worth more than distillers grains alone. We also see an increase in free oil availability and distillers corn oil recovery. Those two are amazing in their own right. So when we summarize this, we have a unique approach of continuous dewatering throughout the entire process that improves the efficiency of the evaporators and the dryers. Let's face it, as an industry, we've done an amazing job of mixing corn and water in the first part of the process. We've gotten really good at separating the ethanol from the corn and the water through distillation. And we're working on perfecting, separating the rest of the corn from the water. And that's the back part of the process. But the way we approach it can either cost us more energy and lower our CI or raise our CI score, or we can employ ICM's unique approach and reduce your CI score and improve your overall plant efficiency. So we reduce natural gas usage. The way we package this together requires lower capital investment. We see a lower operational cost, and we produce very high quality feed products. That's the end of the presentation, and we're ready for questions if there are any. All right, Tom, we're ready to turn it back over to you. Well, I don't hear anybody, which means that either we've done an amazing job answering all the questions along the way.
Okay, can you hear me okay?
We can hear you now, Tom.
Okay. One of the first questions I've got here for you is whether or not the advanced processing package came along from, more serendipitously than in terms of the CI reduction benefits. Did ICM, and this is kind of a tough question maybe to tackle right out of the gate, but as ICM produced these various platform technologies, SMT, FST, FOT, and TS4 over the years, did you guys envision it having a carbon reducing effect, or was it primarily made for diversifying, products and maximizing revenue, and just sort of, as I said, serendipitously led to this lower carbon effect? Can you speak to that?
Wonderful question. Probably one of the more in-depth ones that I've had along the way. What I would say is that the answer is yes, that we did approach this to reducing CI score, but there is some serendipity here, and that is that when we approach this, let me back up. I'm going to use an analogy here, okay? And we look at the ethanol plant as a vehicle to get us from point A to point B, whether it's in time or on a place on Earth here. And you want to get there faster, you can either put a bigger engine with more horsepower in your vehicle. Now it'll get you there faster, but it won't get you there with a higher efficiency. Or you can take a look at how the car is designed. You can make small incremental adjustments to things such as tire air pressure, reduce the weight of the car, reduce air drag on the car. So that's what our approach was, is to take small incremental bites out of this huge demand that the industry, in fact, the world is asking of us. First, not only we don't get to control the price of the corn from an ethanol producer standpoint. So the price of the corn is set, and we really don't get to dictate the price of the distiller's grains or our co-products. So our opportunity is only in the process itself, between grinding the corn and drying the distiller's grains. So we look at it and say, how best can we approach this in incremental steps that each and every producer can afford and can employ or install as it's available to suit their needs. Take, for example, one plant might see a benefit from FOT for oil. Right now, oil's at 80 cents a pound, and they might see that the best thing that they can do right now is contact ICM and ask us how we can improve their oil recovery yield by employing FOT. Or they might be interested in removing fiber and producing just a 50% protein product. Or maybe they have evaporative capacity concerns and they want to employ just TS4 and improve their evaporation. So when we took a good hard look at what we wanted to do for technologies, is we wanted this to be able to be deployed in small bite-sized pieces and not have any stranded assets along the way. There are other approaches to it. You can install technology that makes high protein material, but it's only treating one part of the stream. We wanted to reduce energy consumption along the way and improve efficiency every step of the way. And that starts at grinding the corn and removing that fiber from your fermentation feed.
Okay, well, thanks for that answer. And we're going to get into some very specific questions coming in from the audience, and then I'll jump to some big picture stuff as well. Questions coming in right now. First one is, how do you handle, this is specific, but if you could, how do you handle the additional condensate?
That is an amazing question. And so, yeah, you produce additional condensate. A lot of the plants are pulling in excess water, more so than what's coming in through your CO2 scrubber. So most of the plants bring in all their fresh water through the CO2 scrubber or other areas in the plant, such as like a wash down station, or if they have leaky seals on their pumps. And so you're always bringing water into the plant in one place or the next. Our unique approach to this will take that evap condensate and repurpose it back to areas that you're currently bringing fresh water into that don't need to be clean fresh water. Okay, take for example, it's a way of taking a unique look at things. Take for example, all of our lavatories use drinking water to flush with, but if you're limited on water or how you use that water, we ask the question, is it necessary that that toilet uses drinking water or fresh water to do what it needs to do? And the answer is probably not. So when we look at the CO2 scrubber, you got to ask the question, does it need to have fresh water or does it just need to have cool water?
All right. Another question coming in is related to CDS, and it says at 70% solids, does the new CDS lead to increased scaling as a result of the higher mineral content?
Great question as well. We haven't seen that. Not only did we not see that at our piloting facility in St. Joseph, Missouri, but we don't see that accelerated or amplified inorganic scaling at the facility that's currently running these parameters. In fact, it's quite the opposite. Because of the lower viscosity, we don't see the high fouling on the tubes. So, and then the other approach to this is that when we run more efficient evaporation, we end up reducing our back set. When you reduce your back set, you are de-inventorying those inorganics that you're talking about throughout the plant. So the end result is, yeah, you see a higher concentration per unit of syrup, that you actually see a lower concentration throughout the entire plant.
I'm going to jump to a bigger picture question here, Chuck, and that is, could you identify the largest factor related to CI reduction in terms of your presentation, in terms of the APP package? I have a feeling it's not just one thing, but if you had to, put your finger on the biggest factor, for kind of overarching factor for CI reduction, how would you define that for people?
Yeah, what we're showing here is really drawing attention to continuous dewatering throughout the entire process, which reduces natural gas consumption. See, when we take a bigger picture, or look at the bigger picture, we look at why do we need dryers? Well, to preserve the product. Why do we need evaporators? To manage water load. But why do we need centrifuges? Well, we need centrifuges because neither the evaporators or the dryers can handle whole stillage. There's too much solids in the whole stillage for the evaporators. There's too much water in the whole stillage for the dryers. So we employ amazing centrifuge technology through FOT in our process. And what that does is it allows us to optimize the evaporators so that they're the most efficient that they can be. And in return, we get to optimize the dryers so that they're the most efficient that they can be. And then the two of those summed together show that we're at 2200 BTUs per gallon reduction of natural gas. Now, it also frees up capacity in the dryer because it takes time for that material to dry in the dryer. And the only way that you can dry this faster is to make the temperature hotter, and you can see degradation of products as they go through the dryer at a much higher temperature. There are some amino acids that have thermal instabilities, and then or you limit the throughput. In this particular case, when we start looking at reducing natural gas per gallon, and we alleviate some of those burner constraints or the amount of natural gas that a dryer can actually pull in, it allows you to put more throughput through the same dryer. So not only do we improve the efficiency per gallon of ethanol produced, but it also gives you ability to produce more gallons or more co-product through the same facility.
Terrific. Got a question here related to enzymes. Always tricky to talk about enzymes and yeast, but says if a traditional with the traditional ICM process, what changes would have to be made to implement the advanced processing package in terms of enzymes?
Wow. The last 10 years, I could say that there's probably not a traditional enzyme package anymore. That these enzyme suppliers have done an amazing job of producing custom blends of enzymes to satisfy the needs of each and every plant. And so, but if we do back up and just address what we would assume is traditional as an alpha amylase and a glucoamylase, we're not really requiring any changes to that. We do talk about not really wanting to see proteases used in the process because one of the goals here is to produce as much high protein material as possible. And when we look at using a protease to digest corn proteins to make yeast proteins, that can have an impact on your 50% protein value. And so we don't have a hard stance on that, on the enzyme use, but we do see that you can influence negatively the end product, the PROTOMAX, if you use proteases.
I wanted to ask you a question about your current the current adopters of this technology. I know there's currently three ethanol plants, 3 or 4 that are currently installing the advanced processing package. Can you tell us what, if any, characteristics the early adopters of APP have? I mean, maybe it's hard to pinpoint. Are there certain characteristics these producers have that made them jump on APP sooner than others?
Oh, I don't know that without understanding what the investors at each one of those plants were looking at in terms of market drivers or goals for return of investment for the investors. I would be just guessing at that, but they're out of the 200 plus ethanol plants here in North America, or even more than that. There are some that are so forward thinking that they want to be first in line. Then there's some that are a little less risk adverse. They're not willing to be the first, but they'll be number 1 to be number 2 in line. And there's others that are so conservative that they're okay being the second to the last to install a new technology. So I look at these plants as those plants that are forward thinking and willing to use some of their capital to diversify their products and do it sooner than most everybody else.
Speaking of forward-thinking ethanol producers out there, carbon capture and sequestration is one of the more forward things that is being discussed and pursued. What if any ways does the advanced processing package sort of relate or tie into, if at all, to efforts to sequester CO2?
Yeah, that is a really forward-thinking question, and a good one at that. The answer is that APP or any one of the individual technologies doesn't have any impact on any CO2 sequestration types of technologies out there. So this integrates into your process, and it doesn't have any inhibitory effects of carbon sequestration.
That makes sense. Got a question here from an attendee related to the cost of corn. We're seeing $7 corn, and so you might have to help me out with this question. I think I've got it here, but it says, to confirm, the fiber from the fiber press contains 4% starch. Is this 4% the total starch of the incoming corn? If not, how much of the incoming starch bypasses the firms? Got that? Okay.
Yeah, I understand the nature of the question there, and that's a good one. It's been bouncing around since we started installing FSP back in 2013 on residual starch, and so when we look at, if we're at 4% residual starch on that fiber, and that fiber makes up roughly 1/3 of a distiller's grain pile, most of the starch in that distiller's grain pile is coming from the syrup. So 4% here is actually driving down or can have a net benefit in starch reduction of a distiller's grain pile. So it's a fraction of a fraction is what I'm trying to say here. So that's 4% starch of the 5 pounds per bushel of distiller's grains.
Okay. Let's see here. We have a question related to, we can pop back up. There's a question related to whether or not ICM has ever explored the idea of green hydrogen rather than natural gas to reduce CI. Maybe a little off subject, but care to address that one?
Yeah, it's actually I'd love to take that question. Not necessarily the green hydrogen per se, but we do have other CI reducing technologies such as our gasifier technology, where we're taking wood wastes and turning that waste into a producer gas, and then it goes right into the boiler, and we're offsetting the natural gas demand that way as well. So it's a substantial reduction in CI score by using a gasifier to produce a combustible fuel for the boiler and produce steam that way. Now, off of that steam, you can produce electricity as well, again, lowering your CI score. But I can't say definitively that we've taken a really good hard look at green hydrogen, or at least not that I'm aware of.
Right on. Chuck, I was going to ask you about, there's so many different innovations here with the different equipment. One that really stands out, of course, is the FSD Next Gen Rotary Press. That's just very important piece to the APP, and it visually stands out. It's the thing that kind of people think of when they start to think about this package. That I believe you said that was developed in conjunction with Fournier. Was that adopted from another industry? And on that same lines, have there been other pieces of equipment that are part of this package that have been sort of inspired or adopted from other related processing industries?
Yeah, absolutely. I could say that probably everything in this package is adopted, augmented, improved from other processes or other technologies. And I'm a jump off topic here for just a minute and say that the mousetrap has already been invented years ago. Nobody's inventing a new mousetrap. We just make a better mousetrap, a more efficient mousetrap, a more effective mousetrap, a cheaper mousetrap, right? And in this particular case, we're doing the same thing. We adopted the rotary press out of the wastewater treatment industry and the paper industry, and through the help of an amazing gentleman from Fournier, Francis Cayette, we designed a new version of the rotary press that allows us to run acidic environments and high temperature environments, and doesn't have the high shear between the conveying system and a wedge wire screen that you would see in a screw press. So in the rotary press here, the screen and the fiber rotate at the same speed inside, so there's no shear force, which means that we're not disintegrating the fiber inside the rotary press, which goes counter to what our desire is, and that's not to produce additional fines for the centrifuges to have to remove, or to dilute out the protein content of the PROTOMAX. So we stepped back and took a look at what our goals were, and then went hunting for technology that would achieve it, or technology that we could augment to suit our needs.
Great. Well, it looks like we've tackled pretty much all of the incoming questions. There may be a few more that I can that'll need some defining on that I get you offline, but I'd like to close out today, Chuck, with a question about both the current installations that are ongoing. If you could kind of help us see that picture, what's happening right now. I know there are a lot of exciting things happening with ICM and its clients. If you could kind of talk a little bit about that, and then also, what goals have been set in terms of what are you guys projecting in terms of installations in the near term and long term with APP? What are you hoping for?
Yeah. So what I can say about the current installations is that we have 3 of them that are currently under construction. Just like everybody else globally, we're seeing supply chain disruptions. We're seeing longer lead times than we had in years past, and we're navigating through those. We'll be on schedule to start the first one later this fall. Number 2 will be early next spring, and number 3 would be late summer, early fall next year. And as far as our goals go, we have a unique offering that benefits, in our opinion, everybody in the ethanol industry, and we're here to help every one of these ethanol producers through their technology advancements, whether it's to improve the energy efficiency, improve the plant throughput, improve oil recovery yields or produce a 50% or some other crude protein concentration feed. So, yeah, we would like to see the excitement that's around the ATP process continue not only through this year, next year, but for the next 10 years, I suppose. And then by then, the newer technologies will be rolling out, no different than the iPhone. You start off with an iPhone 1 and a 2 and a 4 and a 5 and a 6. And, you know, as you continue to develop new technologies and improve their capabilities and functionality and reduce energy cost and make them more affordable, the demand goes up for these things. And so we'll continue to develop really amazing technologies. We'll see higher protein concentrations. We'll see higher digestibilities. We'll see some really neat things come out of distillers corn oil, the use of distillers corn oil for just fuel and animal feed probably isn't just the wisest use for that. Of course, you see a tremendous amount of excitement around sustainable aviation fuels. So yeah, we're developing amazing technologies that you'll see come out in the coming years.
Great, that's exciting stuff. Thank you, Chuck, for an excellent presentation. I want to also thank our previous speakers from ICM for making this a great webinar series for us over the last few months. And thank you everyone for tuning in today. We have a few announcements here about upcoming events that I'd like to share with you before you go. Starting in June, we've got the co-located events happening in June at the International Fuel Ethanol Workshop and Expo, the FEW, of course, the world's largest ethanol conference happening in Minneapolis, Minnesota. Co-located with the FEW is the Carbon Capture and Storage Summit and the Biodiesel and Renewable Diesel Summit as well. Those events are sort of an all-in-one package, so if you attend one, you can attend them all, and just a ton of content happening in Minneapolis, June 13th through the 15th. This coming fall, we also have a National Carbon Capture Conference, a standalone event happening in November in Des Moines, and then finally, early next year, the International Biomass Conference and Expo, one of our favorite shows, happening in Atlanta. If you're that show is not just for biomass producers. If you work in the ethanol industry, anything in biofuels, there's a lot of content there for biofuels producers as well. So we hope you can join us for all of those upcoming events. And with that, I just want to thank everybody once again for tuning in to today's webinar. Have a great day.